Hello, and welcome to today's PSU Transportation Seminar. My name is Jason, and I will be introducing and moderating today's seminar. Our Friday transportation seminars have been a tradition since the year 2000. These seminars are usually held live on Portland State University's urban campus located on the ancestral homelands of the Multnomah, Cathlamet, Clackamas, Tumwater, and Watlala bands of the Chinook, the Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. It is important to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place, remember these communities, and to honor their legacy, lives, and descendants. Today, we are pleased to have Brendon Haggerty and Matthew Bozigar presenting Road Noise and Health in Portland, Oregon. Brendon is the Health, Homes, and Communities Manager at Multnomah County Health Department. His team addresses environmental health issues such as lead poisoning, Superfund cleanup, air quality, healthy housing, climate change, and the built environment. He previously served as an epidemiologist for the Oregon Health Authority Climate and Health Program. Matt is an environmental epidemiologist with a multidisciplinary background. He studies multiple adverse environmental exposures, such as noise, air pollution, aeroallergens, radon, and health outcomes such as asthma, cancer, these health words, cardiometabolic risk factors, and diseases. Matt views environmental epidemiology through a geographical lens that emphasizes place and how it affects the health of populations. Here is some information about our upcoming seminars. Next, we'll have Liming Wong, followed by Joe Broach, both also with ties to Trek and Portland State University. For those of you who are PSU students, STEP is a community of students passionate about shaping safer, smarter, and more connected transportation systems and brings together students from across several disciplines for guest speakers, field trips, and other events. STEP is open to all current PSU students, and they're excited to meet more students interested in transportation. If you're interested, please scan the QR code or reach out to ITE STEP. As an overview of today's seminar, you can expect our speaker to present for about 45-ish minutes, which will be followed by a Q&A session. For those of you online, we'll be receiving questions through the Q&A feature on your Zoom control panel. If we run out of time for all of your questions, we will give our speaker the opportunity to email written responses for any questions left unanswered. We have enabled closed captioning, but you must click on the CC feature to view them. We will be recording today's webinar that will be available on our website later today, along with the presentation slides. If you are tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. For those of you in the room, we'll pass around the sign-in sheet so that you can get credit for attending today's seminar. With that, I will hand it over to Brendon and Matt. Brendon and Matt.
Yeah. All right. Well, happy to be here. Good morning, everyone. I'm Brendon Haggerty. I use he, him. I'm the Healthy Homes and Communities Manager at Multnomah County Health Department. And my job today is to give sort of the genesis story for how this study came to be and explain to you why it is that a local health department is taking such interest in traffic noise. But I'm going to start by what I always start with. I've been working at the intersection of transportation and health for 15 years, and I almost always talk about these three main pathways between transportation and health. One is physical inactivity, air pollution, and crash injuries. To elaborate just a little bit, our transportation system is designed mostly for sitting. If you sit too much, you'll get sick or die young. Our transportation system is designed mostly to burn stuff, which we inhale into our lungs. And when we do that, we get sick or die young. And finally, our transportation system is designed to have heavy, fast-moving objects collide with our fragile human bodies, which results in severe injuries or death. So these are the three main pathways that I almost always talk about, but they're not the only ones. And a couple of years ago, Gleisner and co-authors posited 14 different pathways between transportation and health. And some of them are beneficial to health. Obviously, the physical activity that we get when we're biking, walking, or taking transit, that's powerfully protective against most of the leading causes of death. There's other benefits like basic access and mobility. We have to get to the stuff that supports our health in our everyday lives. There are also a number of pathways that are detrimental to health, including the three that I mentioned earlier, and also noise. But why did I pick noise to focus on out of all of these other ones? Well, when I first started doing this work, I don't think I would have. And that's because there really wasn't the evidence. The research wasn't there. But over the past decade or so, we've had epidemiological studies kind of piling up. And now can have a fair amount of confidence in making causal inferences about the relationship between noise and health, and specifically traffic noise and health, or road noise and health. These are some of the health outcomes that can be influenced by noise. And some of them are probably pretty intuitive to you. I think we probably all had the experience of having our sleep disrupted by noise, or finding it difficult to concentrate when there's a leaf blower or a jackhammer running nearby. Some of the ones that are maybe less obvious are these ones up top: cardiovascular disease, hypertension, and diabetes. And I think something I want to point out here is that these are not sort of marginal health outcomes. These are the ones that we are like the most focused on, right? In public health, I work for your local public health authority. In public health, we're focused on leading causes of death. What are the things that are the most common ways that folks die? And so, cardiovascular disease, it's heart disease. That's right behind cancer as a leading cause of death. Hypertension and diabetes. Diabetes is usually in like the number 4, number 5 spot. Often hypertension gets 10 or 11. So these are important health outcomes that we tend to pay attention to. Low birth weight, also very important because it sets kids up for life course health outcomes, right? In that healthy early start that can really set them up. So noise is a contributor to leading causes of death. That's like a red flag for a health department. We also see inequities in the outcomes. When we look at these leading causes of death, we see inequities by race and by socioeconomic status. In this example, you have hypertension death rates by race up on top and by socioeconomic status down on the bottom. And by race, we're seeing that Black residents of Multnomah County experience a much higher death rate from essential hypertension than other racial groups. On the bottom here, what this graph is showing is that folks with less educational attainment experience higher death rates from hypertension. We see a similar story with major cardiovascular disease, where again, we have Black residents experiencing a significantly higher rate. Now we have Native Hawaiian and Pacific Islander residents also experiencing a higher rate. Then similar story with socioeconomic status, which we measure here by educational attainment, where folks with less educational attainment have higher death rates from cardiovascular disease. So to recap, we have noise contributes to leading causes of death, and now we have inequities in those leading causes of death by race and socioeconomic status. When I layer on policy on top of that, I see an environmental justice issue emerge. Because this is a zoning map of the east side of Portland. And then these lighter yellow colors, that's R5 zoning, which is mostly single family. Just loosened that up a little bit recently, right? But what this is showing us is that the most affordable housing types are only allowed on the most congested, polluted corridors. So, for example, you see Sandy Boulevard right here, you can see Powell down here, Division, Hawthorne, 82nd Avenue. And those most affordable housing types, multifamily, to consider like a larger apartment building, are just not allowed in any of the yellow areas. And as we're going to hear about, when we went looking for the highest exposure to noise in the city and the county, what we're finding is that it's associated with these corridors. So it raises questions if the only place that we can build the most affordable housing types is only in the places where there's higher exposure. And I want to acknowledge that there's really good reasons for putting more density on those corridors, right? It's the most efficient way to serve a lot of different kinds of infrastructure, especially stuff like transit. But it is a reality when we start looking at health exposures here. And so I wanted more and better data on this. I wanted to see what was on a granular level happening in our community. And I expected to be able to like call the noise consultants and be like, hey, give me the regular, you know, and there was no such thing. There was no off the shelf thing where they could come, you know, take some measurements in my community and tell me what the picture was. So I guess this is why I go to conferences. Because I had fortuitously a conversation with Matt from Oregon State University. I was talking about this problem that I was facing. I was like, have you ever heard of anything that could work for this? He said, no, but I have an idea. And so that's sort of how the project was born. And what we ended up doing is placing temporarily a lot of these instruments that you can see it's circled there in the yellow circle. They're pretty tiny around the city temporarily over the course of a summer. And I collected a lot of data. We moved them around to different places, so we got some pretty broad coverage. And that was enough. This will be a sneak preview. That was enough to estimate a surface for the whole city, estimate noise levels for the whole city. And so I'm gonna hand it over to Matt to explain more about the findings and how we got there. But I want to make sure that I acknowledge some of the folks who also contributed to this, Max Nonamaker, Abe Moland, and Dan Trafone. A couple of those folks are MERPs, in fact. So you could end up working on something cool like this. But now I'm gonna pass it to Matt to share the findings.
Thanks a lot, Brendon.
I'm
Okay.
gonna sit in the audience so I can.
All right. So I'm Matt Bozigar. I'm an assistant professor at Oregon State University, public health. I focus on epidemiology, particularly environmental epidemiology. But I'm a Portland native, so I went to Grant High School for this. My parents were telling me where they placed a blanket on this particular ledge out front of a building on campus here, where I would play as a baby. So and then of course, because it's a local talk, there's friends and family there in the audience. So anyways, this project meant a lot to me because I am from here and I wanted to understand, noise exposure because it's a health issue in Portland. Okay. So what I'm going to talk about is some more of the technical side of things. Okay, kind of like how we did this, what we did, and so the major part of the talk is going to be about the measurements that we took. So in order to do that, I want to give you a primer on what noise is, just in general, and also how you might measure noise, just conceptually, and then more specifics on what we found here in Portland. And then also some of the, the piece after that is I'll touch a little bit on the noise modeling piece, which is layered on top of that measurement side, where talk a little bit about the methods and the metrics that we're looking at, and then some cool kind of ways, innovative ways to identify the sources of the noise, which is actually kind of tricky. So let me dive into measurement and let me first differentiate sound from noise. Okay, sound is just the vibrations that you sense in your ears. It's a physical thing, right? Noise has an additional, mostly subjective component, but also an objective component too, in that it's both unwanted or harmful. Okay, so noise is sound, but sound is not noise. Actually, okay. Sound is a wave. It has all the properties of a wave. As it approaches an object or a barrier, it's subject to diffraction, refraction, reflection off surfaces. So in the urban environment, there's a lot of dynamics related to this happening. So one other thing about noise and sound is that it's measured on a log scale, and that's because the range of intensities or energies related to the sound waves are so large that it's easier to do this on a log scale. Okay. So, but that means that a 10 decibel increase, you've heard of decibels probably, an increase in 10 decibels is something that you would perceive to be about twice as loud, but it's 10 times the amount of energy as well. So you step that up to 20 decibels and you're talking 4 times as loud. and over 100 times the energy, or about 100 times the energy. So every step up in a graph like this, or in a graphic like this, is going to be a subsequent doubling. Okay, so it's quite a lot of sound energy at the top, you know, those things at the top. And that it doesn't stop there, it continues to go. There's been some events in history that have been well above these levels. So that's a quick primer on sound and noise. And here's how we tend to think about measuring noise. It's challenging because it's dynamic, right? It's changing over time typically. So you're seeing that the black line is a changing of this intensity of a sound or noise signal. Okay, and so one of the ways we might want to measure this is what's the peak sound? Maybe that's or the max sound. What's that might be health relevant for some particular health outcome or reason. We might also be interested in defining the time equivalent sound level. So this is more or less like the average. It's on a log scale though, so keep that in mind. All right, so average sound level. What about like equivalent to the median? So that the amount of time, or essentially that a sound level is exceeded 50% of the time. All right. So and then also something that can capture high noise events also, but not necessarily just the max. So sound levels exceeded 10% of the time, or this L10 metric. The opposite of that is the L90, which is more, 90% of the time this sound level is surpassed. So that would be equivalent to something like a background sound level. Okay. So you can do all of those from just sound pressure metrics. Okay. So measuring the sound pressure levels, that's what you can get. If you want a single average metric that's maybe a little bit more representative of a 24-hour period in which nighttime noise is penalized, because nighttime noise tends to have lower background levels. So any noise occurring at night is deemed to be more potentially impactful. Okay, so there's a 10 decibel penalty from noise happening between 10 p.m. and 7 a.m. for this day-night average sound level metric. One number, but it has a penalty for nighttime noise. Okay, and then maybe something like the intermittency ratio, right? So what proportion of sound energy is happening above some threshold? So that's capturing how pulsing or how intermittent is sound, because that might have unique health effects too. So we're interested in the physical properties of noise and sound, but also really the health relevant stuff is what I'm most interested in. So we're looking at all of these types of metrics. And as Brendon said, the off-the-shelf products were infeasible to start. Okay, and that's too bad, because these types of metrics, or these types of softwares, are very accurate, but you need the right inputs. That's going to model in this type of software the physical propagation of noise very well. Deterministic model, so you put inputs in, you get estimates out. Okay, it's structured. You can also model sources specifically. So here's some of the types of propagation models that we looked into, but that did not work because in our context in Portland, because of these types of limitations. Okay, so we didn't have the correct data inputs. A lot of these models are intended or were built up in Europe, and they have harmonized their data inputs much better. Okay, so they do capture and report the right type of data. We don't really have that necessarily here. Scaling this up to a whole city presents a lot of challenges. So we saw efficiency problems there. We couldn't maybe predict all or generate all the types of metrics that we're interested in either with some of these types of softwares, particularly like the intermittency ratio. And then our initial team lacked some of the noise modeling experience needed to even run these, but our broader team now, we actually have a collaborator here at OHSU, PSU School of Public Health, that is going to try to do a propagation model for the whole city. And then we're going to compare, see how well we're doing with our approach and with an off-the-shelf product. So That's a long way to say that we decided on a statistical modeling approach. So that means that we're using a stochastic process to define a model from the ground up with no kind of like prior like structure necessarily, other than like the type of framework that we're using. And so that meant then we can't use the off-the-shelf products. We're going to use this other approach, but we need ground truth data then, because we can't build a model and have no measured data to validate it with. So that led us to this measurement campaign. So, but then it, you know, the first question is, well, then where do we measure to get representative data to accurately create a model that can capture the parts of the city that we are most interested in, but also the whole city? So, well, our method for doing this was to, we're trying to use a systematic method here, so that when we measure the data out in the field, when we measure noise levels, we can analyze those as if they're a small subsample of the city proper. Okay, so we want it to be representative. We want our sites to be representative of where people are spending the most time, mostly. So we created a demand surface in the geographic information system, weighted by some of the factors you see here. So the time activity patterns as determined. So you're like where you are, where people are during the day mostly. Turns out that's their residence, especially at night, right? So weighting residential areas preferentially a bit. Really being able to capture the whole noise spectrum. So trying to find the quietest spots in the city, but also the loudest spots in the city, so that we can get that spectrum and model that accurately. And that's all, you know, related to land use kind of classification too. So, you know, for example, here's a map of land use classifications for the city of Portland, and you can see like the northern part of Portland has a bunch of industrial activity and zoning, right? And so with our sampling demand surface, right, this is the surface we sampled from. This is the probability that any one of those sites is going to be selected for sampling. Okay, and so you can see it preferentially weighting a lot of the residential areas and less so the industrial area in the north by design. And now sites ended up there still, but they're just over lower probabilities for being selected there. Okay, so this is our systematic method for doing this. All right, so the main objectives for this component were obviously to measure the noise levels, right, out in the field as accurately and systematically as we can, because that's of use, or at least to make it of use for prediction modeling and a whole bunch of different types of people, okay, communities, researchers, practitioners, okay. And we also wanted to compare and contrast the measured data, right? Like this is why we wanted to do this systematically, so that we could make meaningful inference from some of the patterns we're seeing in the measured noise levels. Okay, so compare and contrast by these different socio-demographic, environmental, physical environment, built environment, you know, factors. Also wanted to determine if there were different clusters or noise profiles occurring in the city for certain types of like noise exposure similar in certain areas or not. So we did a cluster analysis to identify those. And then we looked at everything spatially, including the clusters that we identified. So, you know, a huge shout out goes out to my research assistant, Carson Maurer, who's now doing his PhD at the University of North Carolina in biostatistics. But, you know, he was the leader essentially for a lot of weeks in the summer we were doing this and played a big role. So we wouldn't have this, I mean, he's the first author on this paper too. So we wouldn't have this work if it weren't for him. So, and also Brendon's team. But anyways, so what we use out in the field were you know, Brendon mentioned this too, is these low cost devices, but they're also highly accurate. This is actually a new technology, digitally recreating some sounds dynamics in measurement. And so that allows it to be quite small. It's also brought the cost way down. The benefit, the upshot of this is that we can collect highly accurate data for up to a week at a time on battery. And at 1/8 resolution. Again, that's that response of that microphone. That class 1 microphone is really good. So we leveraged these and we obtained permits from some local agencies that we could go out and put these on poles, and we're going to show this picture too. So we put these, 10 to 12 feet up, and we chose poles that were closest to sites that were selected in the site selection process. Okay. And that was quite a fun time, I would say, to go around the city. And even being from Portland, I learned a lot about all these corners of Portland I never knew, about. So it was pretty fun. And so on the result of this is this relatively unprecedented data set of a billion data points. Okay, so 217 sites, short-term sites were selected. There were 9 more long-term sites that we monitored for a whole year on private properties. 37 of those were in parks. Again, that was to try to get good data on gradients into a park of noise decay from a major road, maybe on one side, and also the quietest parts of the city. So, in terms of metrics, we from these little building blocks, 1/8 pieces, we can calculate almost any pressure-based metric we want. So that's a big upshot here. So all the ones I talked about, and more importantly, the daytime and nighttime combinations of these things. We're particularly interested because it's a big gap in, particularly in the US noise epidemiology literature, the nighttime noise levels and sleep disruption and that pathway. All right, so setting the stage for future epidemiological analyses, hopefully. And here's some of our tabular results, big unwieldy table, our metrics across the columns, and down the rows, the total sites, but then also broken out by land use and in public parks specifically, or long-term sites specifically, and then kind of proximity to roads. And you don't have to really look at that in detail because we're going to start to unpack this some more. That's a lot to look at. And this is one of our first kind of key findings, is that just from the measured data, right, we see that there are environmental injustices in exposure. Okay, so the lower your income, right, the higher average noise level, right, and the more non-white the census tract you're living in, census data, the higher the noise level. Okay. So it's more or less mirroring, the health impacts that we're seeing by these similar groups that Brendon was mentioning. We haven't done the, specific epidemiological studies on that yet, but we're on the way. And then for intermittency ratio, we didn't quite see the same pattern. So we saw some evidence of environmental injustices, but only for particular metrics. And of course, we can look at everything spatially. So this is the average noise level with a nighttime penalty again, right? This is our day-night average sound level, DNL metric. Different types, different levels, right? Based on where you are in the city. We looked at daytime noise specifically, we looked at nighttime noise specifically, and we looked at intermittency ratio and a lot of other things. But at this scale, I would argue it's not very useful, right? So kind of need to zoom in and to get a better picture and really understand what the data are telling us. Before we do that though, I just want to show the results of our cluster analyses. So cluster analysis essentially found 4 distinct profiles. Okay, so we put our noise metrics into a big machine learning framework to help us do this. And up to 12 different metrics. Okay, and when we did that, we saw how they varied together or not, and came out with this. All right, these 4 clusters. Now I'm just symbolizing these by the intermittency on the y-axis and the average noise level on the x-axis, and you see that there's some groupings here. We'll talk about these. If you look at different metrics, there's still groupings. So there seems like there's patterns emerging in these profiles that are consistent. So y-axis is your background noise essentially, x-axis is your peak noise events. The nighttime and daytime levels here had really good agreement, right? There's high correlation, so they're on that kind of 1-to-1 line-ish, or at least a line of correlation. And then, you know, nighttime intermittency. This is one of the things that we can do is calculate the intermittency only at nighttime and correlate it with the intermittency during the daytime. Okay, that's a lot, right? There's a lot to unpack here. These are very granular, you know, patterns potentially. We can look at these spatially. So these are all the clusters and where they occur spatially. All right, so it's a lot, and there's a table at the bottom, but I think it's helpful to kind of walk through the clusters one by one. So I'm going to show some information first here. And so we've got, you know, that first panel that I was talking about, the cluster panel. The clusters are listed here, and then I've got some zoomed in areas and the distance to roads on the bottom. So if we walk through the clusters one by one, this cluster 3, the blue one, is one that has higher noise, but moderate intermittency, okay? So higher noise, moderate intermittency, okay? And then where is it tending to occur? Closest or closer to the major roads. That makes sense, I think, right? Like empirically, we would expect noise levels to be higher when you're right on a road. But the intermittency, we've never really had a good grasp on, I would say, at least in a US city. And then it's only moderate, right? So why is that? Why is it not high also? Probably because there's more constant traffic flow. Okay, so that's keeping levels higher, but not necessarily having these big changes, okay, over time. Second cluster here, green one. This was characterized by low average noise levels and high-ish, moderate, high, you know, intermittencies. Okay, where did those occur? Those occurred in the most kind of residential, if you want to say that, areas, right? The furthest from the main roads. But you're still getting moderate intermittency in those locations. It's interesting. And it gets really interesting in the last two clusters. So this fourth cluster, the purple one, you know, we're talking moderate noise, talking higher, in fact, the highest intermittency. Where did that typically occur? Somewhere in between, right? The former two clusters. So not super far away from a major road, but not super close necessarily either. So why is that more intermittent then? I mean, I have a couple of hypotheses. One is just that like there might be a narrow gap where there actually you might be able to see and also hear, you know, cars going by, and on a main road further away, maybe there's some small gap, and every time a car goes by, maybe that's propagating noise and you're getting some intermittency. Another theory is just that the loudest vehicles like trucks and buses, the noise is carrying further, and so that's coming out in pulses of noise as those go by a bit more sporadically. Okay. But we don't really know for certain. And then our last cluster is also really interesting. So spans the whole range of average noise levels from some of the quietest to some of the loudest in the city, all characterized by consistently low intermittency. Well, why is that? And it's interesting here because if you see this panel on the left inside this box, that's Mount Tabor Park. And a lot of this type of cluster, this noise profile occurred in the parks, but it also occurred in the busiest transportation corridors of the city. So this is like the interchange I-84 and 205 there. So why? So obviously the busy transportation one's going to be higher, like on the average noise level. The parks are going to be over here, but both have low intermittency for different reasons, though. So one is because they're very far from roads, right? Especially in like the middle of the parks. So you're not getting much pulsing of any noise. And the same is for when you're right next to the freeway. because really you have a high level, but it's kind of constant, right? That's, I think, the main takeaway. So that's at least what we're thinking. So in the few minutes that are remaining, so I want to make sure to leave some time for questions. Let's talk briefly about some modeling that we're doing. So mainly the objective here is to predict noise at high spatial resolution, but it's more than that. We want to see if we can find alternative data streams that might help us with our prediction. Okay, so incorporating some diverse types of data, and also experiment with different methods to try to really pin down sources. Okay, I can talk a little bit more about you know, how this translates to what the type of noise that we're measuring, we measured and found in the study, but in a second. But this, you know, big shout out here goes to Dr. Andy Larkin at OSU, who is a tremendous data scientist and analyst, and helped develop a land use regression model to predict more or less average noise, 24-hour noise, over a citywide at 10-meter resolution. Okay, so he did that using this land use regression framework, in which he developed some novel predictors that went into the model. So really incorporating the 2D physical shielding dynamics. So taking a point and determining how much the roads around it were essentially shielded or not. So less shielded being louder, right? Or predictive of something louder. And shielded meaning, okay, you're being blocked by a lot of the noise, so probably going to be lower. Turns out those predictors were really important in the model, and it's really well-performing model, even the land use regression. You know, 89% of the variability explained by this model, and residuals, you know, weren't too far away from. So this is our model data and the measured data. So I'm just assessing the correlations there. And then, you know, our preliminary map is from this model. I want to emphasize it's still preliminary, which is why we haven't released it publicly, because we're doing some more work. And we're trying to improve on that by incorporating multimodal data, as I mentioned, in a machine learning framework. So so this work is led by Suhas Sumukh, who is an AI master's student at OSU. And he's incorporating these types of data in a deep convolutional neural network model. Okay, that's a CNN. And taking the land use regression data, predictor data, same kind of tabular predictors, and augmenting with aerial imagery and point cloud elevation, high resolution, 1 meter, you know, elevation data. Seeing if this helps to prove prediction accuracy upon what we had before. And the early results, because this is happening right now, are that it does. And so it's reducing prediction error and bias. Okay, so root mean squared error is going down from 2.5 decibels to 2. That should be dB, not CB. Okay, so it's getting more. Yeah, we're seeing where it's more accurate, particularly benefits from the point cloud data. So the elevation data are like actually very important in predicting the noise levels in this framework, and we're expanding our suite of noise metrics. So not only, right, the previous map was just a 24-hour average sound level, but we have now the ability to calculate essentially all the pressure-based metrics. So like nighttime intermittency. We're going to have a surface and maps for each one of those types of metrics, similar to what we have for 24-hour LEQ. And then there's, of course, this cool stuff that Andy's been doing, identifying sources from other data streams that we collected, data types that we collected at the measurement sites when we put up and took down these sites. Okay, so the videos that are able to identify the sound sources and say what it is, and also images there on the right. So we took photos, we took videos, we took audio, and we recorded the sound pressure levels at every one of the sites to help us in this effort. And this is ongoing. Okay, so the takeaways that I would like you to leave today, you know, having learned. Portland has a very rich measured noise data set now, which is super cool because actually it's quite unique and not many, if any, US cities have something similar. Okay, it's available to people for our partners. There's evidence of noise exposure injustices. Right, you add them on a lot of the other injustices that are happening for marginalized communities and low socioeconomic communities. And you get, you start to have to ask the question, how are these synergistic as well? Right? So noise and air pollution, noise and, whatever else it is. So, and we saw some evidence that there's kind of like 4 different noise profiles occurring in the city. Right, so are those health relevant is the next question. Are those profiles health relevant? Something that we want to study. Alternative but publicly available data streams may really help in places, now not necessarily Portland, but maybe the surrounding metro area, maybe other parts of Oregon, Northwest, more broader. Maybe point elevation data can really replace a lot of like the data hunting and data mining to get all these predictors, when something like that might be highly predictive. So soon we'll have the 12 metrics. So similar to what we had for that one map, we'll have for all 12. And so I mentioned this, like now we're enabled to do some more detailed studies, whether it's environmental justice related or epidemiological. And I gotta say, our collaboration, academic and local public health authority, has been so constructive and productive. So that it's something to just encourage a collaboration, right? And you never know what you're gonna talk about at a conference, and see what all of this came out of that. Just talking. So, and of course, as Brendon said, I would like to thank the Multnomah County team in particular. And also our Oregon State team and our collaborator at OHSU, and the Boston University folks also had a lot of input and a lot of expert advice. And our funding came from via the county, Multnomah County, but it's ultimately a US CDC grant. Okay, that's it for me. Thank you. I'm happy to take some questions, or we can go.
All right, thanks, Brendan and Matt. For those viewing the webinar, please feel free to submit your questions using the Q&A feature in the control panel on the bottom of your Zoom window. Those in the classroom can raise their hands. I'll let the 2 speakers kind of choose on some folks. And then with a few minutes left or so, we'll transition and we'll take some questions from those of you online.
Go ahead.
Okay, thank you. This is great. I really enjoyed it. And when you got to one of your later slides and you used the term multimodal data, and as a transportation person, as soon as I saw the word multimodal, my mind goes somewhere else than multimodal data. I'm thinking different transportation modes.
Yeah.
So I started to wonder, maybe this is a future other analysis and collaboration in terms of data that you can add to your model to improve prediction. Like I instantly thought, well, what if you put in transit? So you have roadways, but some of them are transit routes with buses. Some of them are designated freight routes. They're going to have higher freight traffic. The city of Portland does have data, some data, I think, in their traffic counts about relative freight versus et cetera. Because that, as the planner, then I start thinking about if you include things like that, would there be a way then to predict, like if we made our transit fleet quieter because it's electric or et cetera, to change the noise levels?
Yeah.
So
Yeah.
Anyway, I guess maybe that's a question of the possibilities of what other things you could be.
Yeah, I think it would, in this approach, we'd want to do it, more empirically, like what's the noise level of an electric bus going by, right?
Yeah.
And
Yeah.
so probably want to do it kind of that way. But a lot of what you said in terms of like the data that went into the predictor data, we did use a lot of that stuff actually. So
okay.
a lot of stuff that was on open data, Portland Open Data, GIS, that site. We essentially used anything that was potentially relevant, including, emergency routes, trucking routes, commuting routes, but then also the specific, it's reflected in the traffic counts that we use as well, like the fleet mix at any location. And
okay.
that was all actually in there.
Okay, great, good to know. Thanks.
Yeah.
Yeah, question, so on the map, I'm old, I can't read the
Yes, ma'am.
legend. Yeah, or, yeah, but Brendon showed it, but, so you have red, what, like, is that, what does red mean? Is that a time weighted average or of what? And is that, I assume it's not health linked, so is it, why is it red? Like, I know you're trying to show it's higher, but it does kind of allude to that these are above some type of health, suggested health levels.
I tend to like a monochromatic map for this reason too, right? Because it doesn't emphasize certain areas maybe you don't intend to, but this particular map is a 24-hour average. So essentially just taking all the measurements every day, 24 hours, and averaging them. So there's no penalty for nighttime noise in this representation. So it's a prediction of the levels, and what's red is just essentially the top of this scale. It has no other empirical.
But we don't know if that level is above.
It's not above
some
it,
type
right.
of- Right, so. Okay.
I mean,
threshold
I think, EPA recommends, I think 45 indoors and 55 outdoors, I think, but that would be hard to achieve.
Yeah.
probably.
And that's higher than the WHO recommends outdoors. I think it's in the 40s. And so really, if you're looking at who's exposed to noise, it's like a lot of Portland. And so it's a good question though. You can call me.
So I'm kind of interested in this over time also, and for a few reasons. One is where I live, like I'm getting much more sensitive to noise as I get older. I totally appreciate this research. I'll notice that when there's certain kinds of weather, sound will carry more. I'll be like, wow, it's so noisy outside today because of the pressure or whatever. The changing in seasons when the leaves fall off the tree, all of a sudden it's so much noisier. Reflections. It seems like that to me. So I'd be interested in some of that. Also, I remember reading sort of French study about exposure to noise, like in Paris or something like that, and they were like, one person riding a motorcycle with a modified exhaust is going to wake up 10,000 people. So I wonder how much effect it over time, as people modify their exhaust, intentionally trying to make as much noise as possible. Just one person can have such a huge effect versus just an industrial area that's sort of similar all the time. Anyway, that's my question.
Yeah, so absolutely right. And then, my mind also goes straight to the street racing that's happening a lot in Portland in the middle of the night, right? With engines that are modified and extra loud. And I know what you're talking about, the little it was a video, I think, of a motorcyclist going through Paris. And so one of the things that we did was we measured at the long-term sites, and we found that seasonally there were differences in the average noise levels. You have big differences too by if school's in or out. Traffic is at different times of the day when that happens, more or less in summer, right? And then intermittency is also changing over time. And there's a big component of change over time based on leaves on the trees, as you said. So we should probably get some more funding to keep this going.
One event that I forgot to bring up too is when this leaf blower ban takes effect on January 1st. I wonder, that would be an interesting point to think about.
Oh yeah, totally. I'll have to think about that.
Intermittency one. Yeah, we'll go with Eve and then we'll get back there.
I have a question about the four noise profiles that emerged or clusters. First of all, are those, do those something similar show up in other research as well, like research from the EU or elsewhere? And do you have thoughts about, you mentioned how you were wondering about the health relevancy of them? Do you have predictions? Do you have thoughts about what you find, or is that coming up in the future?
Yeah, it's great questions. About the clusters, as far as we know, that type of information hasn't existed before, whether in Europe or anywhere. So there's been other people that have done kind of like cluster-based analyses, but in totally different ways and with different metrics and, you know, more over time, like focused on like when clustering was happening over time. So I don't know. As far as I know, it doesn't exist. And then remind me what the other question was.
The health relevance.
Yeah. I really have no idea. You know, I think one of the burning questions in this field, the noise health field, is how much does intermittency matter? How much do frequencies matter? Like the same pressure level, right? The same intensity of a sound, two sounds are not equal if one's, you know, at a low frequency versus a high frequency, or at a certain frequency that's particularly annoying, or particularly maybe has frequency specific effects as well. The timing of the noise matters, and we're finding nighttime noise is very important. The cadence, as I mentioned, so like we're kind of we've known about noise. Noise has been around ever since, you know, especially we moved into cities as a species, right? Like the Industrial Revolution, and since then it's been there, but put on the back burner because other things have been more pressing. And then, you know, fast forward, and Europe's ahead of us in terms of research right now, and they're leading the way. And we're trying to catch up and answer some of these questions, but we really don't know. So I don't know. I think intermittency probably plays a big role at nighttime. So maybe it's disrupting sleep more. There's a study that's soon to be published. Maybe I shouldn't say this, but it's about pink noise and like white noise machines at night. And you know, there's no research on that. So all the people that were buying these noise machines and stuff, and kids are listening to them, infants, you know, and there's no evidence for that. And so, yeah, so that's not looking as healthy as it is in masking noise, because you're creating more noise. That will be coming up. Not by me.
We have a question back there.
The first efforts in Oregon to address noise as an environmental justice and equity issue happened about 15 years ago with the North Portland Noise Study and early noise mapping in the United States by Greenbush and Associates out of Seattle for the city's noise review board and for the city of Portland. How did that work, which was groundbreaking work, that set the tone for this type of work today, help inform your work?
Yeah, so help to inspire the scale. So we wanted to expand the scale, and incorporate new equipment, because we have these amazing new monitors, and it's not just like that brand. There's other brands too, where we can match the quality, but with way less cost, and you know, do it even more systematically. So yeah.
Were you able to incorporate data on road material or building material into analysis?
Yes, yeah, great question. At least road material. Road material was in the GIS database that we had access to, I think. And then, you know, building materials, I don't know, other than, you know, this is why we want to do the imagery-based models. And we want to expand to do street level imagery as well. So to help pick up some of those patterns, like if it's like gray concrete, can it pick it up? And we know that that's going to reflect, you know, a certain amount of noise or absorb a certain amount of noise, versus like a timber siding, or like wood siding or something, like, right? So we want to go in that direction with buildings, but with the roads, a lot of that I think was in there.
We work our way back up, Zachary, and then David.
Okay, to the context, I work at an organization called Oregon Walks, we do pedestrian advocacy, and by nature of my job, I get to walk in these spaces with like electeds or making transportation choices, and like freight lobby and AAA lobby and industry lobby, and then back to sanitation and climate lobby, right? So in those spaces, you know, on the hierarchy of things that people are talking about, there's like, you know, congestion and safety and greenhouse gas emissions, these things, right? And the noise is somewhere like over there, right? It's not even on people's radar. And thought first of all, I'm inspired by all of you being here and by you all doing this. It's really great because it seems so critically important, right? And so I'm curious if you were able to take some of this information and then extrapolate it into like quantifiable health impacts that can maybe take it from over there and bring it into the scale of, we should be paying attention about this and we should be finding resources to mitigate those harms. That was kind of the first question. The second question is, and it's potentially out of scope, but is there a way of pricing that you all found in your research, pricing the impacts of noise? Right now, it's just a negative externality that lands on everyone's shoulders and inequitably. So pricing it, and then what are some of the interventions that you come across that are effective and I hate to sound like a Debbie Downer, but like and doable?
You want to tackle any part of that? Cause I have, but I've been talking a lot.
Yeah, well, I might take maybe the first part of your question is like, where does noise fit in and in terms of how influential is it on health among all of those pathways that I mentioned from between transportation and health? And I think like everyone should leave here knowing and thinking that the physical activity one is the most important one. That has the preventive effects of that are really dramatic. Probably close behind air quality and safety or traffic crash injury. But we don't really know how much this fits in. Like, if transportation is causing X percentage of major cardiovascular deaths, what portion of that is caused by noise? Open question.
It is, and it isn't, like in the US, in the US context, we really don't know. But in Europe, right, so there's a metric called the disability adjusted life year, the DALY, okay? So it's years lost of healthy living due to something, okay? And among all environmental factors that we're exposed to, or people in Europe are exposed to, after air pollution, the number 2 cause of death and disability is from noise. So ahead of things for all sorts of things, chemicals, lead, you name it. That's now. That didn't used to be the case, but that's now. So we collectively need to do a lot more research on this topic to quantify the things that and that's where we want to go, quantify things more concretely, like what percent of morbidity and mortality in Portland is due to noise versus other things. It means measuring air pollution really well too, because that's like, they're from the same sources oftentimes, right? Like transportation sources. So really partitioning out those effects and you have to get highly granular to do that on a highly local scale. So because sometimes, you'll be blocked from noise, but you might not be blocked from air pollution in the same way or vice versa, in the urban fabric. But the evidence is there in Europe, and we're slower to catch on to it, and we need to raise more awareness about it.
I wanted to ask at this 10-meter scale, like it looks very localized to corridors. How should we think about like distances here? Like how much does perceived loudness fall off over the scale of, a 10-foot lane or a 200-foot block or?
So it depends on the built environment. Okay, so whether you've got a hard or a soft surface, basically, is it a natural surface versus like a man-made surface or a water body? Okay, so that's one thing that's going to affect it. But then there's a very clear distance decay. It's quantifiable. There's an equation. It's like this is the amount to be expected, decay in your noise over distance, and so that goes into the physical propagation modeling software. It's built into it. But it's also why you need these other data inputs, right, to do that. So what you see at 10, at this scale zoomed out is it just looks like all the the roads. Like it's not that interesting at this scale, quite frankly. Like you see some city level patterns, you might be able to find the quietest places on in the city, and it tends to be like parks, but you zoom in and you start to see the block, the blockage of sound at individual buildings happening across the city. And that's where it gets like much more interesting in my opinion. You start to see those dynamics happening. But
I mean, I think this is interesting because our zoning changes so abruptly with those corridors. So
there.
Yeah, I think I keep trying to form a question in my head and sort of failing, but I'm in the transportation policy space. And I think it's really, I'm grappling with all of the different layers that go into these types of things and just like optimum health. And you know, in transportation, we frequently are trying to sort of decrease the distance people need to go to get to the things they need or want to access, or increasing their options of doing that walking, biking, and the positive health impacts that can have. But I think we also are seeing that, you know, if you live right on the busiest road that is closest to all those things, there could be a negative health impact from noise. And so I'm just thinking through like the policy or like outcomes of this. Is it land use? Are we focusing on how to keep the proximity but lowering the
Yes.
mitigating the noise? Like that's
Yes.
where my mind is.
Okay, thank you. And I realized I didn't answer your third question. Well, we can answer both together now. So intervention, what can you do? Like thinking about primary, tertiary, or secondary prevention in public health. So primary would be reducing the exposure altogether, which would be, maybe that's something reducing engine noises. Maybe it's because a lot of the noise happens from friction on the pavement. Maybe it's quieter pavement, so a built environment, a lot of stuff with vehicle specific or built environment. But also secondary prevention, so that'd be primary prevention. Secondary prevention would be blocking noise essentially from like where it's being generated from and you. So that can be like building materials again, sound walls, stuff like that. And then the last line of defense is tertiary, where it's like your person almost. So like earplugs and white noise machines, you know, insulated windows would be like secondary prevention as well. So those are like your options when you start to think about it, like that kind of stuff.
All right, we have a couple of minutes left, so we'll take a couple of questions from online. One that shows up, you mentioned the data being available to the community and public. Are there any spatial data sets or the sound data set that are publicly available for folks to see or use?
Not yet, but they will be soon. Yeah, so I think that's the best way to answer that.
They're not posted.
Yeah.
But like contacting either Matt or myself is a good way to get your hand on.
For transportation practitioners, what, if any, mitigations would you suggest based on your findings?
You know, I don't know, like, I like what Paris did, like they you know, installed a whole network of like very fancy monitors essentially that are able to capture like photographs of vehicles and record their sound levels. And essentially the city, you know, decided they wanted to find people that were breaking the noise law. Like, but you know, in order to get there, you have to have like noise laws to begin with. And so I don't know, like maybe, I think we're still in the phase of like raising awareness about the issue and showing that it's a health issue. But I wear earplugs, like that's something you can do, like, but not everyone can if you've got like, you know, young children or you need to hear emergency sound or whatever, so.
I think it's also maybe to layer on that, I think for folks who are in the planning and policy space, I think it's a really interesting question to ask, how far away from a loud road can you get? What's possible in our neighborhoods, in our built environment? And there are real policy levers for that.
All right, we have time for maybe one or two more. Have you compared your data with the data from the Bureau of Transportation Statistics, transportation noise pollution?
Yes, I have. And the first thing you notice is that like almost all the places where people actually live have no data. And that's exactly why I couldn't use that product for this work, because that model is made for highway engineers and things like that to help determine where they need to put noise barriers and stuff like that. But it does not at all really transfer without a lot of extra effort to apply that same model citywide, which is a bigger undertaking and we weren't here to do. But yeah, so the missing data gaps are their only, data is like on the main transportation.
One more quick one. So you mentioned, I think it was Paris and having maybe some form of automated enforcement for noise.
That's a good way to say it, yeah.
Yeah, are you aware of any other places that do that? And does it operate like a, automated speed enforcement program or red light running program?
Yeah, great question. I don't know of anything like that. But I know there's other things that cities have done, such as like having quieter pavement, citywide, making quiet zones, adjusting speed limits dramatically, limiting traffic, building more soundproof buildings in areas where that's going to make a difference. And but not that per se outside of Paris. No.
All right, fantastic. So thank you all again for joining and attending today's Friday Transportation Seminar. For those of you remotely, after the seminar ends, you'll have an opportunity to complete a brief survey about today's event. It only takes a couple of minutes and we would really appreciate your feedback. So if you could please complete that survey. Please join me once more in thanking Brendon and Matt for their presentation today.